In this video, I'm going to be going over quantum circuits and how they're represented in visual diagrams, and I'm going to finish with some important examples. So here we can see a quantum circuit that's composed of 3 CNOT gates. So these white lines here are your wires, right? Each one of these is a CNOT gate. So this CNOT gate has wire slash qubit 0 as the control with wire slash qubit 1 as the target. Here it's flipped, here it's the same. And unless stated otherwise, it's safe to assume that the input to a quantum circuit with n qubits, so here 2 qubits, right, is just going to be the computational basis state ket 0 tensored n times, right? So if we have 2 qubits here, that would be this, right? And then that's just ket 0 tensor product ket 0, right? Which is exactly what this state is here. And so let's see what this circuit above is actually doing, or what it's actually computing, given some arbitrary 2-qubit computational basis state. So we're assuming that the input is a computational basis state, meaning that x0 is either a 0 or a 1, and x1 is either a 0 or 1, right? This qubit is either ket 0 or ket 1. This qubit is either ket 0 or ket 1. So what we're going to do to figure this out is, given this initial state, right, ket 0, ket x0, x1, right, which again is just, right, it's just the tensor product of the two. So we're going to figure out what it actually does to this input state. So first we're going to apply this first CNOT gate where the control is qubit 0, wire 0. So we go ahead and do that here. That gives us psi 1, right? Our input state is psi 0. So what does that give us, right? So it just passes the control wire along, and then it XORs this wire 0 with wire 1. So that's just exactly that, definition of CNOT. Now we're going to apply the second CNOT controlled on wire 1. So that means that whatever's in wire 1 is just going to be passed along, right? And then we're going to XOR wire 0 with what's in wire 1, which is exactly what we're doing here. And then if we just XOR this qubit with itself, right, if x0 is a 0, then if we XOR it with 0, it's just 0, so it leaves us with x1. If x0 is 1, then XORing it with 1 gives us 0, and then XORing 0 with x1 gives us x1. So this just simplifies to x1, and then this we're just carrying that down. So this is the state that we're at now, at this point in the circuit. And now we're going to apply this last CNOT. So just, your typical CNOT controlled on wire 0. So your wire 0 gets passed along, and then we're going to XOR wire 0 with wire 1, which is right here. Same thing as above. These cancel, so x0 is what's left, and so we're left with this state. And so what we see is that we started with x0, x1, and we finish with x1 and x0. So what this circuit is doing is it's swapping the states of qubit 0 and 1. So this circuit is canonically referred to as the swap gate right here. And that's exactly what this diagram is here. So this is just a simplified version of that, which you'll see in a lot of diagrams in literature. Additionally, suppose that we have some unitary linear operator u, right? So that's just saying u is a valid quantum gate. We can then define a controlled u gate. So we're just extending the controlled NOT gate. We can make the controlled unitary arbitrary. So as one might expect, this unitary has a control qubit, right, just like in CNOT, and n target qubits. In the specific CNOT gate, we only have one target qubit. But if we just have an arbitrary unitary, that acts on n qubits, we can have that as well. So if the control is 0, nothing happens. If the control is a 1, then U is applied to those n target qubits. So the CNOT is really just a special case of this unitary where U equals X, right? So if I draw that out, this is our control wire. This is our controlled U acting on these n qubits in its circuit diagram. And so then, right, if U equals X, then the CNOT gate as a diagram is just this, right? We have one target qubit, one control qubit, and if the wire is a 0, it does nothing. If the wire is a 1, then it applies an X gate to this second wire here. And another important operation in a quantum circuit is the measurement operation. And so this is denoted by this meter symbol here. You'll see that in a lot of literature as well, followed by these two lines here. So these two lines extending out just it's just notation to say that what this operation produces is a probabilistic bit, right? So we'll call that M. And then as we know by now, this probabilistic bit M is, you're going to read a 0 with probability mod alpha squared and 1 with probability mod b squared, right? Because if this arbitrary input is this superposition of 0 and 1, right, then this is going to be a classical bit where you read a 0 with probability, right, mod square alpha squared, or mod square alpha, and a 1 with probability mod square beta. And so let's see if we can figure out if we can come up with a circuit that copies a quantum state. So we'll start by figuring out how to do this on a classical computer. So how can we copy a bit on a classical computer? Well, this is very easy, right? We can just use the classical analog of the CNOT gate, where the target bit is just initialized to 0. So you can just think of it as like a template that we're going to draw on. So it's pretty simple, right? If X is a 0, then we're just going to XOR X with 0, and we'll get X, which is 0. If X is 1, then we'll XOR 1 with 0, and then we'll just get 1. So either way, you start with some arbitrary bit that's a 0 or a 1, and this empty register or bit that's just initialized to a 0. You just perform an XOR, and you'll get X in that register or that memory location. So can we do the same thing on a quantum computer? Which is to say, given a qubit 0, right, in the state, qubit 0 meaning it's the top wire in the circuit diagram. Not that the qubit is in state 0, but qubit 0 being the 0th qubit of the quantum computer. So let's say we have some qubit 0 that's in superposition, right? Can we copy this same state, this qubit state into the second wire, so qubit 1, initialized to ket 0, right? It's just the analog of this classical version we did up here. So that's to say, can we go from this state psi 0 to psi? So the input state is written as, right, psi and 0 is just ket psi tensor product ket 0. We just expand ket psi, distribute this tensor product here, and what we end up with is this state here. If we apply a controlled CNOT, right, controlled on qubit 0 to this state, what do we have? What do we get? So what we end up with is this state right here. And so is this what we wanted, right? So did we create the state psi? Well, the state psi, let's figure out what that actually is, right? Because that's what we're trying to figure out if we can get over here. We applied CNOT to this. We're trying to see if that equals this state here. So psi, right, is just psi tensor product psi, expand them, distribute them, and what you get is this state here. So clearly these two states aren't equivalent, right? So applying CNOT to the state psi 0 does not copy the state psi into wire 1, or into our second qubit. So we failed to copy the state. And so later we're going to show that it's actually impossible to copy the state of a qubit when we go over the no cloning theorem, which I'll do in a later video. And I'm going to now go over the Bell states and the quantum circuit that's used to produce these states. So the 4 Bell states, I listed them here. These are the Bell states. These come up a lot in quantum computing, so you'll probably be seeing these quite often. And so these states are the result of passing the 4 computational basis states through the following circuit. This one right here. So applying a Hadamard to the top wire, and then a controlled NOT from wire 0 to wire 1. And we can see that this circuit diagram can be written as an expression, right? Is just applying a Hadamard to wire 1. This is kind of sloppy. This should be H tensor product with I, right? Because we're only applying H to this wire, and then we're leaving this one untouched. And then we're following that up with a controlled NOT gate controlled on wire 0. And we can actually express this in this equation here, as this equation, which is a function of x0 and x1, which are either 0 or 1. And so we can see that using this equation here, which is just a reflection of this circuit diagram, right? If we pass in 0, 0, right, the computational basis state 0, 0, out pops out this Bell state, which we noted up here, and then we can just do that 3 more times. If you just want to pause the video and just check that you can actually pass those into this equation and verify that. But yeah, so that is the idea behind quantum circuits in diagram form, with an example of the quantum circuit that creates the Bell states. I hope this was helpful, and thank you.